Okay, so tonight I will talk about stars and life. I prefer this title to Science and Faith, which could be quite general. There will be two halves to the talk. The first half I will talk a little bit about my own life, growing up, studies, and then I will talk about stars and my work. And in the second half of the talk, we'll look at the relation between my faith and my work in the context of science and faith. And then at the end, I'm very happy to answer any questions you might have. I don't have all the answers, but I'm happy to try answering them. Okay, so before I start, I have to do a disclaimer that my work is scientific. I am not studying the relation between science and faith. So this is kind of one of the hobby or things that have cropped up in my personal life, but not as part of my work. So in order to prepare for the talk, some people know I don't like reading. So I'm not going to pretend I read all these books, but half of the books. And this is the list I've taken. I would definitely recommend this one, so if you want to have a look at those books afterwards. But my main goal by looking at reading a few books was to have some books in favor of science and faith and some against. So to have a balanced view. I think it's always important to understand how the other side or how the other people think if we are going to discuss in a productive way. Because a lot of discussion involving faith and science is people talking at each other, but not really knowing what are the sticking point from the other side. So that's what I also will try to do in terms of how scientists who are atheists see faith from their point of view. Okay, so again, the books will be here at the end if you want to come and have a look. I'll put up the biography at the end as well. Okay, so let's start at the beginning. This is a Google map, and the idea is you might not be able to see the detail, but this is a map of Switzerland. And the main point is that you can see all the green. So I come from a small village called Sugnan with 200 people. This is what the church I used to attend as a child. It's a Protestant church, which is roughly the equivalent of Anglican church, but not the same. And what you can see also is the nice view of the Alps. For those who like mountains, there's Matterhorn near Zermatt and Mont Blanc here, so 1 hour away from the mountains. And we don't have a sea in Switzerland, but we have lakes. So this is a running joke in the family. Okay. This is me as a child. So sometimes it's funny to see people, like you meet people, you remember their faces. So that's what people in my village remember me as. I was a worryless. I had more than I deserved. I always think I've had more in life than what I deserved. But my goal in life is to try to make the most of what I've received. But never really worried until much later. Okay, then as I grew up, I had to decide what to do. So I grew up on a farm, and the only thing I knew is I was not going to be a farmer. Many people think, a farmer is a dream job, but the reality is it's very tough. And even though I like the countryside and the fresh air, I never could wake up in the morning early, and I never have enough physical energy to be a farmer. So then I had to decide what shall I do. So I like sports, and I was good in school, but being good in school is generally not popular when you're about 10 to 15. So I enjoyed sports, not so much school, but I still had to decide what to do. So the career advisor at school told me, you should just continue your studies because you're good at it. So I went to the A-level equivalent in Switzerland called Gymnase. And then at the end of the Gymnase, I still had to decide what to do. So one day I was working in the cereal collection center in the middle of the countryside, and I could see lots of stars. So then I decided, let's study physics to understand stars. Because I like chemistry, physics, and mathematics. So I had to make a choice. Okay, so then I went to Lausanne, which is just at the tip of the Lemon Lake, for my undergraduate studies and masters at the EPFL, if you know about it. Then I moved to the end of the lake to Geneva Observatory for my PhD. And then after that, I moved to the other side of Switzerland, which is Basel, which is the Swiss-German part of Switzerland. It's like a different world when you come from the French-speaking part. So it seems like a small step, but it's a big step to go to Basel here. I did 2.5 years in Basel, then I came to Kiel about 11 years ago as a researcher, and I was just promoted to professor this January. Okay, now let's go into space. Enough about my life. So we are sitting on Earth, which is the third rock from the sun. So we have 4 rocky planets, followed by 4 giant gas planets, and the sun is our reference star because it is the closest star. But it's actually a small star. But let's look at the importance of star in the universe, and that's usually how I start most of my talks, because this shows the entire evolution of the universe as we understand it now. So we have the Big Bang on the left, about 13.7 billion years ago, and we have now on the right. And the Big Bang is basically, as it says, a bang, so rapid expansion, until about 400 million years later, the first stars are able to form. And the first stars end what is called the Dark Ages, where matter was decoupled from light, and the universe was actually quite dark. But from that point onwards, stars formed, galaxies formed, evolved, and then lots of things happened. So the stars that formed here have died or have collapsed a long time ago. So we mostly see stars from here, but what happens at the end of the star's life is that they explode, is what we call supernova explosion. And here you have an image of 1987A, so maybe some of you remember. This was a nearby supernova explosion in the large magnetic clouds that could be seen by eye in the southern hemisphere. In some extreme cases, the explosion is bipolar, so it's not a spherical explosion, but 2 powerful jets. And they are called gamma ray bursts. And some gamma ray bursts have actually been observed. So the light was emitted roughly at this point in the evolution of the universe, about 600 million years after the Big Bang. And light traveled all this while to reach us. So even though we can't see stars from very early on in the evolution of the universe, we can see explosion that took place a long time ago when the universe was still young. So that means that we can use stars and the explosions as probes of the evolution of the universe over a wide range of time. Then after a supernova explosion, not everything is destroyed. The core of the star actually forms what we call a compact object, which can be a neutron star or black hole. And sometimes you have 2 neutron stars nearby, and then they're going to merge together. When they do merge, they start bending space-time, and they emit what is called gravitational waves signal. And in the recent years, we've been able to observe the first such mergers of neutron stars and black holes together. And it is a very exciting time in astronomy. Okay, so you're probably all familiar or have seen once a periodic table. Stars are also the laboratory where most of the chemical elements that are around us have been formed. So hydrogen and helium and some lithium is formed during the Big Bang, the initial burst. But all the other elements, for example, iron here in our blood, or the oxygen we breathe, the calcium in our bones, were created in stars, some stars, during some point in the evolution. And part of my work is to understand which stars form how much of all these chemical elements. Okay, we've looked at the importance of stars. Let's look at a few properties now of stars. As you might have seen in the sky, the first property I want to look at is the color of stars. You will have noticed some stars appear more blue, others more red, and some just appear to be white. And what the colors of stars tell us is the temperature at their surface. So blue stars means that their surface is hotter than red stars. They're still all very hot, because a red star would be a few thousand Kelvin, a few thousand degrees, whereas a blue star might be up to 100,000 degrees. So it's still much hotter than what we experience here. Another slide that I really like to look at is comparing the size of stars. So we are here on Earth, which compared to the other rocky planets seems quite big. But then if we compare the size of the Earth to other gas giant planets, we see that the Earth is very small compared to Jupiter. Now Jupiter stands big on this slide. If you go to the next panel, you see that Jupiter is quite small compared to the Sun or other stars called Sirius. Now this large star is then still very small compared to another star called Aldebaran. Then Aldebaran now is tiny compared to the star known as Betelgeuse, and this is one of the stars in the Orion Nebula. Now Betelgeuse is still not the largest star. The largest star that we know of is VY Canis Majoris, that has a radius 2,000 times that of the Sun, and that is larger than the distance between the Sun and the Earth, so 10 times this distance. Just imagine, just so that we picture the size of this star. Now I've shown you the slide about the universe. Our galaxy has about 100 billion stars, and the universe has about a billion or more galaxies. So just to, in terms of scale, we are here, and we have stars, and then the universe is still much larger. Okay, so now you might think I spend all my nights at the observatory on Keele campus. But actually, even my colleagues who do observations do not spend most of their time behind the telescope, because most observations are done via computers. They are done in sunnier places than Stoke, as you can imagine. So the main telescopes are in Hawaii, Chile, the Canary Islands. So I sometimes get asked to go to conferences in these very exotic places. So last year we had the chance to go to Reunion Island. It was a good experience. But actually what I do computer simulations of stars. So I don't even do observations in my work. I use the general equations of physics. So I will spend the next half an hour on these equations now. I hope you're ready. Now, just to show you some equations, it always looks scary. We basically use concepts like conservation of energy, momentum, and mass that you would have learned in normal mechanics, and we put these equations into a computer program, we apply it to stars, and then we are able to compute how the structure of the star is and how it evolves with time. Okay, that then allows us to predict how old the Sun is and how it will evolve. So let's look at what do the computer models or theory of stellar evolution tells us about the evolution of the Sun. So the Sun is actually a middle-aged star. It's like 4.5 billion years old, and it's got another 4.5 billion years to burn its rest of hydrogen in its core. So in total, a hydrogen burning phase lasts about 9 billion years, so we still have some time left. But what will happen next? Once all the hydrogen will be burned, the core will contract until the center is hot enough to burn helium. And as a result of this contraction, energy is released in the outer layers, which are then expelled or pushed further apart. And at this point, the size of the Sun will be almost similar to the distance between the Sun and the Earth. So that will be a major problem for life on Earth. But what is even more a problem will be the radiation, so the light emitted by a star when it will be what we call a red giant. Okay, and so that's why it's going to appear more red and also more extended. Okay, so what is left at the end? So we said we burn hydrogen into helium, then helium, when the core is hot enough, can burn into carbon and oxygen. And stars like the Sun will not be able to burn more fuel, so they'll end up as carbon, oxygen, matter, and then they will become what we call degenerate, and this is the stage what we call white dwarfs. So you might have heard the term white dwarf. So the Sun will end up as a white dwarf. It's a very compact object, and it's very bright and hot, and the light emitted by the white dwarf will push away the outer layers and produce very pretty pictures for us, which are called planetary nebulae. Okay, so the planetary nebulae is kind of the end state of a star like our Sun. My favorite kind of stars are more massive than the Sun, more than 10 times the mass of the Sun. Actually, I run simulations of stars that are 500 times the mass of the Sun, and they're still useful. But what happens in more massive stars, the main difference is you not only burn hydrogen into helium and helium into carbon, but you also have more fusion stages, burning elements from carbon to silicon into what are called iron group elements. So this is elements like nickel, cobalt, iron. And because elements around iron are some of the most stable elements in the universe, you can't extract more nuclear energy out of it. That means the iron core will collapse into a very compact object to the point where neutrons and protons will almost touch each other. At this point, this inner core is very stiff, and therefore more matter will fall on top and will bounce like a tennis ball on the ground, and then that will launch what is called a shock wave that will produce the supernova explosion that I mentioned before. Okay, and then this is the pretty picture we end up with at the end. So this is the Crab Nebula. So this is the remnant of a supernova explosion that occurred in 1054 and that was observed by the Chinese astronomers. And we have different groups of supernovas. The two main groups are supernovas from massive stars that have the subscript 2 or 1 BC, whereas white dwarfs like our sun need a companion to gain more mass before they are allowed to explode as supernova, which we call type 1a supernova. Okay, so what are we left with at the end is very compact objects. I've mentioned white dwarfs. Massive stars produce neutron stars or black holes. And just to realize again the mass and the size of these objects, if we start with white dwarfs, which are supported by electron degeneracy, they are roughly the mass of the sun and in the size of the Earth. Okay? So the sun is roughly 100 times in radius that of the Earth normally. And then if we then move to neutron stars, this is now where neutrons are packed very tightly. They have about the same mass as the sun, but now the radius is only about 10 kilometers. And finally, if there's even more gravity, gravity wins and we form what is called a black hole. And there is no real radius for a black hole, but the radius we know is smaller than about 10 kilometers, and the mass is generally more than one mass of the sun. So my question for you now, since you all had some tea, you probably put some sugar in your tea, but now you have to go on a diet. So let's say you don't put sugar in your tea anymore or coffee. You're going to say, I'm going to put neutron star matter in my tea. So you're going to take 1 teaspoon from a neutron star and put it in your tea. My question is, how many cars put together would have the same mass as a teaspoon from a neutron star? Okay, so I'll give you 30 seconds to do the maths. So when you're ready with an answer, please shout your answer or raise your hand. Do we? Sorry? 200. 500 million. Do we go higher, lower? 47 trillion. 22. Any other? 100. Okay, the answer is 100 million. Okay? That's assuming that a car is about 1 ton and a teaspoon is 1 cubic centimeter. Okay, so just to realize how dense a neutron star is, if you could take 1 teaspoon out of it, it would have the same mass as 100 million cars put together. So you have this amount of space and 100 million cars. Okay, so generally when I do computer simulations, I try to simulate the entire structure of the star from its center to its surface and throughout its lifetime. But I have to do some serious approximation when I do that, so it's simple models. So what I have then started doing is try to do more detailed simulations that focus on a small part of the star. So hope you can see the star in the background and a small square here. So I've started doing smaller scale simulation. They're still large scale, but small part of the star, and only simulate for about a few hundred seconds, whereas the lifetime of the sun, for example, is billions of years. But these kind of simulations are much more expensive, to the point that these simulations that I'm going to show you on the next slide would have taken 85 years on this laptop, right? Well, because I managed to use a supercomputer in Durham, it only took a few months. Okay. And right now, we are running simulations in Barcelona and using, on average, 20,000 computer cores to run simulations for a few months. And our budget for 1 year is 40 million computing core hours. Okay. So now you have to be impressed when you look at this. So as I said, it's represented, the small square in the previous slide shows the part of the star that is simulated. And what happens here is that there is carbon burning at the bottom of this layer. This produces a lot of heat, and when you heat up gas, it's going to go up and rise by a buoyancy force. So this is the simulation domain. And the questions we want to answer is, how far does this strong mixing go up to? And the colors here show the speed at which the gas flows. You can more or less see or follow the flow of the gas here, right? It's going up and then you're turning. At some point you see almost loops. We also want to know what is the shape of the transition layer at the top. Sounds like a detail, but it's very important. Okay. So I cannot do all this work on my own, so generally I'm involved in large projects. I'm just going to mention two such large projects. The first one just finished last year, and it was called SHINE. So whenever I spell SHINE now, I think of putting a Y instead of, and it stands for Stellar Hydrodynamics Nucleosynthesis, which is the creation of chemical elements in stars and evolution. It was funded by the European Union. It was a budget of 1.4 million euros, and it lasted 5 years, could fund about 4 extra people working with me. And one of the things we produced was the movie on the previous slide. Okay. And then at roughly the same time where the first project stopped, I started another project, and this is what is called a cost action. It's funded by European countries, so not exactly the European Union. There's a budget of about €500,000. We try to increase it every time, so I think now we're going to reach 700,000 euros. It's running for 4 years, and the main goal of this type of work is to coordinate research. So we have scientists, more than 200 scientists, scattered across European countries, so we have 30 countries involved. And what we organize is mostly meetings and collaboration visits so that we can exchange ideas and work together across Europe. Okay, so that's the end of the first half. So as you can imagine, I often get asked questions. You might not guess the second one, or you might guess the second one, we'll see. But the first one I'm usually asked is, why do you do your job? I mean, it looks interesting, but it doesn't seem useful at all for everyday life, right? It's usually polite, but just like scratching your... So, I mean, I would say, especially in the context of science and faith, for me, my main driver is curiosity. I'm curious. The reason why I picked physics, in the end, I wanted to understand stars, or at least try to understand. So my main driver is curiosity. But I think there are side products, like many things. So for example, I'm never worried about the students who start spending 3 or 4 years of their life doing a PhD with me, because then they are very well prepared to run complex simulations, model complex situations with computer programming. So in a way, what we study is maybe less important for everyday life, but how we do it and how we push the boundaries, our own boundaries, is a key skill for life. Second question is Stoke. You came from Switzerland and you came to Stoke. Well, I wanted to show you the green space in my village, because I'm also from a village, so I could not survive in London, and I'm quite happy in Kiel. The Kiel campus is very nice if you haven't seen it, and also the Kiel Observatory is open every Tuesday night, so if anyone is interested in going to see the stars, you can turn up any Tuesday, rain or shine, or rain or moon. There's always somebody there, and also sometimes Saturday afternoon. So you can check all the info on the website. So if you Google Kiel Observatory, every Tuesday night it's open. Okay, the third question often is, do you believe in God? You're a scientist, so surely you don't believe in God. So then they are very surprised when I say, yes, actually, I do believe in God. And then come the next questions. But doesn't science contradict faith? Can science prove or disprove the existence of God? If God exists, how can there be so much pain in the world? This is not directly related to science, but actually it's also an important question. And how does your faith combine with your work as a scientist? So I'll try to answer these in not exactly the same order. I also have my own list of questions that I ask. I still ask myself, or I used to ask myself, am I working too much? The answer is probably yes. But you'll see why I put this question there. What are the purpose and meaning of life? I think that's, again, I'm curious, so I'm not just interested in understanding the structure of stars, but also the meaning of life. How will it end? I think that's also quite a useful question. I think possibly the one question that for me I had to answer, and in terms of relation between science and faith, is, are we more than a complex random combination of molecules, which is kind of what you would be if you consider the theory of evolution, right? So these, I think, for me, were the driving questions throughout my journey. Okay, so let's go through the contradictions between science and faith. I think it might not be the most important one, but the first one that comes to mind usually is the creation versus evolution story, right? In Genesis, it talks about the creation of the universe in 7 days. And there is clearly a conflict with what I've just presented on other slides when I talk about billions of years for the evolution of the universe, or even the age of the sun, compared to the creation story, if we take it literally in 7 days, or to say that the whole universe is a few thousand years old. So my personal view on this is that the Genesis story is not to be taken literally. It describes in a very nice and executive summary the different purpose and places or realm that we have around the Earth and also in space. I put in square brackets here about the work-life balance, because for me a key aspect of the Genesis story is how should I balance my work life, right? And the idea of the seventh day needs to be a day of rest. So I try to apply most of the time at least 1 day of rest, often if I can 2 days of rest over the weekend. So I think there are always multiple stories. I would say that, of course, there is this first apparent contradiction, but you don't need to go into science to spot apparent contradictions in the Bible. If you look at different stories, if you're really critical, you can say, oh, this was in this order, that part was in that order. So, and I also put them as apparent because they're not necessarily real, but you can definitely spot contradictions in the Bible if you look for them. So to me, then, the way I understand that is that we cannot interpret the Bible literally, at least not its entirety. This can then become a very slippery slope, because you can say, okay, then I can interpret anything I like, I just keep the parts that I like, I throw away the rest of the stuff. But the 2 points to make on this aspect. The first one is, even if people say they follow the Bible literally, they are still interpreting what they read to translate it into their own life. So I think we interpret the Bible in any case, even if we think we take it literally. The second point, I think we can have the core principles that are the 10 Commandments and the resurrection story as literal. And then there are other parts that are actually designed to be interpreted, like the parables. In the New Testament, Jesus never talked straight in clear words. It was always via a story that had to be interpreted to be understood. Okay, the last point on this slide is a quote that is often made by atheists who like science more than faith, is that science is about fact while faith is about belief. I don't fully agree on this quote, but I think it starts showing that science looks at certain aspects while faith at other aspects. And definitely we consider a different point of view from these two sides between science and faith. So they're not concerned about exactly the same thing, and they don't have the same approach. Okay. What most people would agree probably on is we need a proof. And atheists say that we have an incredible claim, and therefore it requires an incredible or strong proof. So let's just review the incredible claim in a few sentences, right? We have this God who created the universe. We know now how big it is, how old it is. And then this God came on the earth as a man to die for our sins so that we can spend the rest of eternity in heaven with him. And that God who created the entire universe cares about each one of us. And it is an incredible claim, right? Whether we believe in it or not, it remains an incredible claim. So I personally would agree with the fact that we need some proof about it. Okay, so let's look at proofs. And I would say that there is no scientific direct proofs, but I will explain why this is the case. And there are 4 aspects of science that I would like to mention. First 2 are about the scientific method. My point of view is that in science, I assume, when I do my work in science, I just assume that God doesn't exist, or at least that God doesn't interfere with my equations, or He doesn't change the laws of physics in a random fashion, right? Because otherwise my theories would not be very reliable. And so that's one point. A second point is that scientific experiments or results need to be able to, we need to be able to reproduce them, and then other people must be able to follow the same steps and reproduce the same results multiple times. So it must be reproducible. So I'll use the word reproducible to say that we must be able to repeat the experiment and come up with the same outcome for the scientific result to stand. The third aspect is about probabilities. So that's the idea that a result is never really yes or no. So generally a result is given either with an uncertainty or probability. So a probability is between 0, meaning 0 is no, 1 is yes with certainty. But actually there's no, I don't know any scientific results where you can have p equals, so the probability equals to 0 or the probability equals to 1. So then in the scientific context, we can ask the question, what is the probability that God exists? And can science prove it or not? And some people start by saying, science cannot answer this question, therefore the probability that God exists is 50%. You can't prove that God exists, you can't prove that God doesn't exist. But most atheists would say that the probability is much smaller than 1 because there is little scientific evidence for the existence of God. Okay? The one important fact to remember about probabilities is not because a result has a very low probability that it is not possible. So you can have a very small probability, but this can still be the right answer. And I don't think there are any scientists who say that the probability that God exists is strictly equal to 0. So it's negligibly small, they would say, but they wouldn't say it's 0 because it's very hard to prove that something doesn't exist. They turn it around and say, this sentence, that an incredible claim requires a strong proof. The last point about scientific method, and I'm talking more about natural sciences, is the uniqueness of a solution. So you might show that your solution works. I'm going to give you some example. But there might be another solution to explain the same result. So uniqueness of a solution is even harder to prove than the existence of a solution. All right, so we talked about 4 key elements in the scientific method. So one, that assuming that God doesn't exist as a starting point, the fact that we need the answers to be reproducible or results to be reproducible, the concept of probabilities, that it's very rare to have a probability of strictly 0 or 1, and the difficulty of proving uniqueness. Okay, so that's why I'm going to say that there is no direct scientific proof of the existence of God because of these properties of science. But I think there are very good indirect partial proofs. Okay, the first one comes from history. So history, I think there is enough records to prove the existence of Jesus as a man, as a prophet. But why doesn't it belong to a strong scientific proof? Is first, so it would be elements like the resurrection. You can't really reproduce the resurrection on demand, right? Jesus died and rose only once, so it would fail the test of reproducibility. Okay, but obviously from the historical point of view is definitely a proof. The next topic is prayer. And I think the main problem with prayer is first that it's generally misunderstood. But atheists would say that there are studies, scientific studies, that have proven that prayer on average doesn't really help, or there's no statistical significant improvement linked to prayer on when they did careful experiments. But what is prayer about? I think we all fall into the trap that prayer is, we use prayer as a voucher system. I still do it every day. When I pray, I ask God for this, that, and this, and please do this for me, please do that for me. If we consider prayer as a discussion or a way to communicate with God, and the communication will only fail if we stop that communication, but it will not fail when we don't get the answer that we want to hear. Okay? So that, I think, it depends how we see prayer. The second aspect is praying in tongues. So this is not a common phenomena, possibly in all churches, but the first time it appeared is at Pentecost. So it's written in the New Testament. When Peter and a group of people were praying, suddenly they all started speaking in weird languages that they had not learned, and everybody thought they were drunk, and so on. But this is actually one aspect where I would say it is somehow reproducible, because I don't pray in tongues or speak in tongues, but I know lots of people who pray in tongues regularly. So if I were to ask them, can you pray in tongues, they would say they could do it. Not me, but other people can do it. And I know lots of English speakers who can't really learn another language, and they speak in a weird language without learning it. So I would say that's nothing short of a miracle. Which brings us to the topic of miracles. Okay, why is miracles not an effective proof of the existence of God? And there are several aspects. That's why I explained the aspects of scientific proof. You probably would have guessed by now what is not working, or why are miracles not an effective proof. The first, before I give you the answer, let's imagine I pray for somebody in this room and they get healed. So we witness a miracle in front of our eyes, right? So we know, we have proof that the miracle just happened. Let's just say we took the scans before, we have the scan after, right? And we have clear proof. Two things is reproducibility, right? Can we reproduce this miracle on demand? The answer is no. And the other one is, do we have a unique solution for this miracle? The answer is also no. We cannot prove 100% that God did it. We can say we prayed about it and this even happened, but you can't say from a scientific point of view that actually that is a proof of the existence of God. You can say you prayed about it, then the person was healed. But it's not a strict proof of the existence of God. I think a very effective proof is personal experience. So I will share with you my personal experience. So I grew up in a Protestant church. I went to church. And as a teenager, I didn't have my own proof. So that's why I say I need a proof as well. So I stopped going to church. I didn't believe God existed for quite a few years. Then I went to Japan for industrial training. That was just before I started my PhD. I was out of my comfort zone, so I had time to think about the big questions of life. And I actually asked God, I need a sign. If you exist, I want a sign. And the sign he gave me was somebody in the streets in Japan holding a sign saying, Jesus is here. So it was actually, you could say this is not a scientific proof, but I didn't even stop. So the person was in a place, in a square, holding a sign in English in the middle of Japan. They're probably still wondering why they were holding this sign. But for me, because I had asked and I passed by this person, that was sufficient proof for me. That was my own personal proof and sign. And again, why are these personal experiences not scientific proof? Because they are not reproducible and they don't apply. They're not also unique. You wouldn't prove that God exists just because I saw a sign. Another interesting one is altruism. So in particular, we have pastors giving up their comfort and comforts of life or more doing ministry at work, and they give up a huge part of their life to help others. Now, you might explain part of it with evolution theory, saying that if you help your neighbor, you're going to help back. But it's harder to explain when you try to help people at the other end of the planet who can't really help you back. Okay, so that's quite hard to explain when you're giving. So I would say one of the best proof as Christians is to give to others when we can't get paid back, because that's kind of we're really paying the price of our faith. A funny one on the list is orchids, so it might be odd one out, but when I look at an orchid flower, I really think it's prettier than it needs to be to survive, right? Evolution theory would say that you would need to be pretty to survive as a flower, because you need to attract the insects so that you can be reproduced. I just don't think orchids just fit that pattern. The last point, and I think it's a key point, is the concept of free will. If science clearly agreed with faith and everything was clear and we knew the answer already, there wouldn't be free will. And the concept of free will is that we have a choice and we won't know the answer until we die. So we have to take a step of faith, and that's why it's called faith, right? We actually have to guess partly without knowing the answer for sure. Okay, so I've talked a lot about proof, the concept of proof, and what are my own proofs, why are they not pure scientific proofs. I think if we discuss with scientists, we have to be, we remind ourselves of what constitutes a scientific proof. Let's now turn to science, because science also has its limitations. And that would be, for me, the main point, is that science cannot answer all the questions. And if you remember one thing from today, I hope you'll remember the how versus why, is that science is very good at answering how does a star evolve, what is the structure of the star, but it's not very good at answering the question why. What is the meaning of life? Why are we here? Or why is gravity proportional to 1 over r squared, right? Science can tell us, yeah, gravity is proportional to 1 over r squared, how the Earth goes around the sun, but not why was it designed like this or made like this. When we talk about pain as a proof against the existence of God, so if we have a good God and there's bad in the world, then we could say that this is a proof that God doesn't exist. But we can also look at science in the same way. If we look at nuclear weapons, if we are not careful, then science can also be used for bad, not just religion. And I think when bad arises, it's generally because either people are greedy or they have a desire for control or they want more. And control, I think, is a very attractive feature of science. Because if you have a scientific fact, you're in control because you know that that result can be reproduced. So you can count on it to behave in the way you expect it all the time. So it's very good in terms of control. Okay, there are also contradictions in sciences. One of the famous one is particle-wave duality. So light, generally you know that it's a wave, but in some cases our theories have to treat light as a particle. On the other hand, most objects around us are treated as particles, even electrons, protons, or neutrons, but sometimes in order to understand their properties or their behavior, we have to treat them as waves. This is part of the topic of quantum mechanics. We won't go into the details, but there are also apparent contradictions in sciences. Again, this is not a proof that God exists. It's just a point to make that scientific theories are not complete and not also always black and white in science. Things are evolving with time. Okay, there are also lots of scientific things that we can't see. So for example, well, at least most objects or topics we study in astrophysics are not seen by eye. So the first aspect is either light at extremely high temperature or high energy or low energy The common example is the UV light that burns our skin, or infrared radiation that keeps an environment warm, like the greenhouse effect. We also have neutrinos. Did you know that you have 1 billion neutrinos crossing every square centimeter of your body every second? So it's a huge amount of particles. They are produced in the middle of the sun. They travel towards us, cross our body. 1 billion particles per square centimeter every second, and we don't see them, but they exist. And finally, gravitational waves is a deformation of space-time itself. So it's also something we don't see, but we can measure its effect. Finally, we have dark matter and dark energy. Dark matter is basic matter, but we don't see it. And dark energy is probably a sign of our incomplete understanding of the universe, but the term that explains why the expansion of the universe is accelerating rather than slowing down. Okay, furthermore, many proofs in science are indirect. So for example, we don't really have direct proof that black holes exist. What we see is matter going around the black hole, so we can infer mass, and we don't see light from it, but we can see things falling onto it. So all these parts about science are not proofs of God's existence, but they are proof that science is work in progress, and also that we don't always see what we know exists. Okay, so finally, how does my faith influence my work? I'm going to go back to the science explains. When I do science work, I try to explain how things work, how is a star the way it is, and so on, how is it evolving. And for me, the faith answers the question, why? What is the meaning of life? Why am I here? So I kind of keep them separate most of the time. Possibly, like most people in their daily jobs, we don't think about faith in our daily job, so I don't think about faith in my daily job. But I think there are many parallel or common points between the two. So the first one is that both my scientific work and my faith were driven and are still driven by the search for truth. And there's also the ethical aspects of religion, of science. Scientific has to follow rigorous ethics, and faith in general follows clear ethics rules. Also, both bring me into the unknown, out of my comfort zone. It's something that is sometimes scary, stressful, but at the same time very exciting and makes every day different. Furthermore, even though I don't put God into my computer program, I still pray every day about my work, and like most works, we have a lot of stress. Scientific work is very competitive. We are continuously trying to tell other people that we are better than the competitors, so they should give me more money rather than give it to somebody else. And so in terms of confidence, it's also sometimes quite hard to stay confident because everybody is criticizing our work all the time. And then finally, the perspective is whatever problem I face, I know that God is bigger than any problem I might face, and with my work, I know how big God is, right? It's bigger than anything I can ever imagine. Okay, so my final thoughts are the following. I think for me, one of the key questions that led to my faith was, am I more than a complex, random combination of molecules? Yes or no? I see how science and faith relate, at least in my life, is science answers the question how, and faith why. Why am I here? What is the meaning of life? And now it's time to ask your own questions. So let me just put 2 questions in case you're wondering about these. I really like those questions. They were really tough last time I was around. So thank you for your attention.